every time humanity gets a hold of new laws of physics, we're able to radically change what's possible.
We're starting to take advantage of some of the really, really strange or unintuitive kinds of powers that exist in quantum mechanics, things like entanglement or superposition. But in the new round in quantum computing, we're trying to treat these quantum mechanical effects not as bugs, but as features.
I am troubled sometimes by the knee-jerk view of many. They kind of freeze knowledge as of now and then make all of these, to me, outrageous claims. What they're ignoring here, of course, is the new knowledge that will be generated and will be acted upon.
I think the real national security implication is not having the economic benefits of this technology happen. We need as many smart people as we can get working on it, and we need to give them on-ramps into the technology that are not due a 5-6 year PhD. And with linear algebra and Python and some of these open source toolkits, you can actually get pretty close to the cutting edge in some real engineering problems. You know, it's not that quantum computers are saying, here's all these limits to the computers you could imagine building. It's actually saying, I can do things that you don't understand what it's computing. Like, that's your challenge.
Well, hello, everyone. It's Jim O'Shaughnessy with yet another Infinite Loops. Today, I am delighted to have the very first winner of the O'Shaughnessy Fellowship, which we started this year, Dr. William Zeng, who is the founder of the Unitary Fund, a nonprofit dedicated to an open source quantum computing ecosystem for the benefit of all people. He has a degree in physics from Yale, is a Rhodes Scholar, has a PhD in quantum algorithms from Oxford, co-inventor of the Quil quantum instruction language, has been picked by Forbes in the science category in the 30 under 30. William, I got to tell you, the first thing I thought of when I was getting ready for this podcast was Kennedy's remark about all of the brilliant people he had in the White House at one given time, poets, scientists, etc. And he said, I don't think that there's been this kind of concentration of intellectual firepower in the White House since Jefferson dined alone. Welcome, William.
Well, thank you, Jim. That's very complimentary. But I will say one of the things that's super exciting about working in quantum technologies and quantum information is it's such a magnet for a whole bunch of smart people. I mean, I get to find myself in rooms where I'm the dumbest, and it's just, this is such a hard problem that it attracts so many interesting and really multidisciplinary people. Anyway, we'll talk more about that. But thank you so much for having me on here, and I'm super excited about the fellowship as well, of course.
Delighted to have you on. And as you know from our conversations, I have been interested in quantum mechanics and then quantum computing for a long, long time. We had some great discussions about a particular problem that we're going to talk about a little bit later in the podcast. But first, can you help us out and sort of explain in intelligent layman's language what's going on with quantum computing? Why is it such a massive potential innovation? You have a great quote, which is, every time humanity gets a hold of new laws of physics, we're able to radically change what's possible. And so maybe let's use that as a jumping off point to explain in language that sort of the intelligent layman could grok.
Sure. I mean, you could think of our understanding of physics as the operating system that underlies whatever technology we're building at the time. So understanding thermodynamics in many ways is a part of what drives the Industrial Revolution. Understanding electromagnetism leads to electronics and then information technology. And we've known about, quantum physics for almost 100 years. Actually, I think there's going to be an International Year of Quantum in 2025 as sort of an unofficial 100 years. But the starting point wasn't just one moment. So we've known about quantum physics for a long time. And in many ways, technologies we use today, like lasers or transistors in regular chips, they wouldn't work if we didn't understand quantum mechanics. But the new thing that's happening is we're starting to take advantage of some of the really, really strange or unintuitive or different kinds of powers that exist in quantum mechanics, things like entanglement or superposition, and we can talk more about these subtleties, and use them to basically amplify them into features in technology that we build. So every computer we work on today works with rules of physics, so rules of electromagnetism. And when the chips get very, very small, they're actually trying to avoid quantum mechanical features. But in the new round in quantum computing, we're trying to treat these quantum mechanical effects not as bugs, but as features.
So tell me a little bit. Let's go a little deeper there on what's a qubit? What is different from a quantum computing perspective to the old Seymour Cray supercomputers? I know they're very, very different, but if you could explain the differences.
So what's really fun about it is you really think about the basic model of computing a little bit differently. So instead of having a bit, you have this thing called a quantum bit that behaves somewhat differently. And from a mathematical perspective, you can think of a quantum bit as a generalized version of a weighted coin. So we're going to move in 3 steps. So you can start with a normal bit. It's just either 0 or 1. And then you can think of a probabilistic bit. So that's something like a coin, which if it's an even coin, then it's 50-50, 50% 0, 50% 1. But you can change that. It could be 75% 1, 25% 0. And you can model that as, I guess we're on a podcast, so I'm using my hands. So I don't know if we'll see it, but as a line.
No, that's actually okay, because we also release this on YouTube. So the people who watch it there will get the extra.
Yep. So a probabilistic bit, so a normal bit is just like two points. And a probabilistic bit you can think of as existing on a line between those 2 points, where 0's at the bottom and 1's at the top. And an even coin is halfway. And then one that's weighted towards 1 is maybe a little bit higher up, 75% of the way towards 1. A quantum bit is you representing quantum states using a generalization of probability theory, these things called amplitudes. But you don't model that on a line between 0 and 1. You model it on a sphere where the 0 is the North Pole and the South Pole is the 1. Or the other way around. Physicists and computer scientists flip this, which makes it a little bit annoying. But in either case, the poles are the 0s and 1s. And then the state of the quantum bit is somewhere on the surface of that sphere instead of being somewhere on the line. And one of the ways you can start to think about how this gives you additional power is if you thought about the interval line where a fair coin is just at the midpoint. For quantum bits, there's not just one midpoint. There's actually the whole equator around the middle that all act, when we measure them, like they're fair coins, but they're actually different states. And so there's extra states that you can take advantage of even in a single qubit. And then mathematically, this gets more complicated as we scale them up, and sort of we can talk more about where that power comes from. But fundamentally in quantum computing, you're thinking about a different computing model than what's usually thought about in what we call classical computing. And there's 2 important things about that. One is there's actually some of the original work on these things called quantum Turing machines showed that everything that's computable by a normal computer can be computed by a quantum computer and vice versa. But that's only given an infinite amount of space and time resources, or at least, not infinite, something that scales exponentially. So a very, very, very large number. But if you look at more practical kinds of questions where we restrict the space and time resources, then there are algorithms that are available to quantum computers that can run much, much faster, even exponentially faster. So it's taking something that would be, billions of years on a very good classical computer to something that's tractable on a quantum computer. And that's because the fundamental model's really different.
And give us a sense of the scale of that difference. The old joke. I don't know if you're a Douglas Adams fan, but I am. And he's got the computer that they ask, what is the meaning of life? And it just keeps computing. And because it does, because time and space, right? And then it ultimately gives the answer 42. Talk about the difference between what might take the fastest conventional computer, the amount of time to solve a very intractable problem versus a quantum computer?
Well, one way to look at the comparison is to look at what it would take to use a regular computer to simulate what the quantum computer is doing. And let's think about simulated exactly. And this is where this kind of fundamental scaling difference between quantum and classical starts to rear its head. So if you have n quantum bits, then it's going to take you 2 to the n classical bits to exactly simulate what those quantum bits are doing. So that scales quickly. So something like 10 quantum bits you could do on an old compact from like 20, 30 years ago. Something that's more like 30 or 35 starts to take a pretty beefy AWS, something you could provision on one of the cloud providers. Once you start to get to 60 or 80 or 100, if you're trying to exactly simulate it, then the state of the quantum computer requires, if there's 100 quantum bits, requires 2 to the 100 complex numbers to write it down. And that's significantly bigger than, we're starting to get to astronomical universe size scales in terms of numbers. So that's where the sort of one of the fundamental interests in the power of quantum computing comes from. Now, it's more subtle than that, because in this power example, we're usually not trying to exactly simulate what a quantum computer is doing. We're just trying to solve some problem. So sometimes we can just approximately simulate the quantum computer and still do it much more quickly on a classical computer, even though we have 100 bits. And so one of the interesting races that's going on right now, as some of the first quantum computers are coming online that are in this regime of 60, 100, a couple hundred quantum bits, is to benchmark them and to show that they can do things that classical computers can't do, even while we keep improving the classical algorithms. So there's been sort of this back and forth that's been going on for a couple of years.
So what are some of the things, speculatively, that the quantum computers that can accomplish that a conventional classical computer can't?
Yeah, so I think that we go through sort of 4 categories. The first is one of the original impetuses for building quantum computers, which is to simulate other quantum physics systems. So this scaling of what it takes for a regular computer to simulate a quantum computer doesn't just apply to simulating quantum computers. It applies to simulating other kind of quantum physics systems. So molecules, catalysts, materials, superconductors, interesting states of matter. We know how to write down the theoretical, in some cases, in many cases, actually. We know how to write down the rules for how these things should behave, but it's really hard to do the numerics because of this scaling problem. And quantum computers, sort of, at least you can take intuitively, are pretty good at this. And there are some specific algorithms to do it in detail, but at a high level, you're using a quantum computer as a quantum physics system to simulate some other one. So the first one is in quantum simulation, and that might sound niche, but it's not. We can come back to it. But there's other ones in Monte Carlo simulations. So this is important for risk and pricing in finance, or risk modeling for all sorts of different applications. There's machine learning applications, there's optimization applications, and in each of these cases, there's work that's ongoing and has been done on proving separations between, as well as we can, because it's hard work, as well as we can, between classical algorithms and quantum algorithms. So I can dive into, we can pick whichever direction of those you want to dive into next, but there's sort of a pretty big broad class.
Yeah. So the 2 that I'm most interested in, and I would guess that my audience is as well, would be first the ability to simulate quantum systems themselves, and what we could learn from that in terms of our ability to peer into them that we don't currently have. But then also the use case of simulating risk, and what a quantum computing world might be able to do in transforming the idea of risk, the idea of investment, et cetera. So why don't we cover those 2 first?
Yeah, so the first one, simulating quantum physics systems might sound like a very esoteric or even academic domain, but it can have pretty big impact. So to give a couple examples, so one that people in the field talk about a lot is in catalysis. So a lot of the big industrial chemical processes that we run as a species depend on some catalyst to activate the reaction. And so one really big one is called nitrogen fixation, which is what we use to make fertilizer. And the catalyst one of the catalysts we use for nitrogen fixation was invented. It's the Haber-Bosch process. It's from about 110 years ago. The catalyst operates at 400 degrees Celsius and 200 atmospheres of pressure. So it's a pretty energy-intensive reaction. And what it does, it takes nitrogen out of the atmosphere, puts it into ammonia, and then we use it to make fertilizer. And we do this so much that something like 1% to 2% of the world's annual energy budget goes into this. Wouldn't it be great if we could do better? And we think we can do better. And one of the reasons we think we can do better is there's natural systems, as bacteria, that do this kind of reaction, but obviously not at that kind of temperature and pressure. And we want to understand how. And in order to understand how, we need to simulate the quantum physics of the systems. And there's other kinds of examples. One of them is in trying to understand why photosynthesis is so efficient in plants. There's parts of the electron transport chain that look like they might involve quantum mechanics to really work as efficiently as they do. And it's hard for us to use computers to simulate and study this. You know, if we're designing an airplane today, we don't do it so much on wind tunnels. We can mostly do it on computers because we know the laws of physics and the computer algorithms are good. For materials which have quantum mechanical behavior, like trying to make a high temperature superconductor, we know the rules, but our computers get stuck. And so if we can build quantum computers that are good enough to simulate these, then we can start to unlock, not just the ones I indicated, but probably lots of exotic kinds of materials that we've never thought of.
Again, one of the reasons why I'm so absolutely fascinated by this is just that alone could lead to remarkable innovation and our ability to conquer things that have been really bedeviling us in the past. And, sort of the way all of that reaches in, as you're pointing out, with the energy usage. If we could drop that considerably, that has profound effects on, everything, really, the world economy and all the way down. Talk a little bit now about the more pedestrian, I guess some would think, but also very important element of how it might be able to transform the idea of risk, our analysis of risk. Why is it potentially better than what we have with a classical computer?
Yeah, so I've been looking at using quantum computers. So actually, one thing that's probably worth saying is quantum computers are not better at everything. I just said that at the outset. And we're talking about specific examples because there are certain things that we know quantum computers are going to be better at, sometimes a lot better, but they're not just better at any generic problem, like word processing. It's not unclear to me then that'll be better in a quantum computer. But actually, until recently, I had been leading an advanced computing and quantum computing research group at Goldman Sachs, and we've been doing a lot of work looking at risk and pricing applications of quantum computing. And one of the reasons we look there is there's a type of algorithm for Monte Carlo simulations that has a proven speed up for quantum computers over classical. And this is what we call a quadratic speed up. So typically Monte Carlo converges, the number of samples you need to take to get to some error epsilon converges as 1 over epsilon squared. So if you want to get to an error of 1 in 1,000, you need to take 1,000,000 samples, dropping some constant back. But the quantum algorithm scales as 1 over epsilon. So if you want to get an error in 1 in 1,000, it's 1,000 samples. And if you want your error to be, 1 in 1,000,000, then instead of being 1,000,000 squared sample, there's only 1,000,000 samples. So it's 1,000,000x speed up there. Now, that's just in theory. And the constant factors really matter. And you need to worry about, what do I mean by a sample? If the quantum computer's samples are much slower than each classical computer sample, then the speedup doesn't gets washed out. But the fundamental improvement is there. And we've done a bunch of work in estimating, what specs of a quantum computer you'd need in order to make that practical. And then in terms of, the business applications, it's that we can, with a fixed compute budget, just know our models more accurately in the same amount of time.
And that kind of leads me to the the speculative world of science fiction, et cetera, where everyone is making elaborate claims about, whoever comes up with the first quantum computer will rule the world because of all of the things that it can do. What's the reality? What's the reality of when serviceable quantum computers dependably come online? What does that world look like?
I mean, I think our best analogy is to look at what happened when the first round of computers came online. So a few synthetic takeaways. One is, it's not about building the quantum computer, and then you have the quantum computer and you run things on it, and it gives you all these advantages. There'll be a bunch of different product lines from a bunch of different places with increasingly better quantum computers, some of which will specialize for different applications, but they're only going to be barely good when they first start getting applied. They're not even barely good now. I'd say that the quantum computers we have now are basically good enough to say they're quantum computers, but not too much else. So I think there's going to be an on-ramp. And, economically what will happen is the folks that figure out how to apply them first will reap a lot of benefits from that. But eventually, like other technologies, it'll start to spread, and then we'll all benefit from the general improvement. Now, there is one asterisk here, which is maybe worth mentioning, which is there's a particular application of quantum computing that gets talked about a lot, which is in code breaking. And there's an algorithm for prime factorization that's from 1994, and that spurred a lot of initial interest. And there could be even more first mover advantages. The concern is, we have a long way to go. You need a pretty good quantum computer in order to run an algorithm to break a key in 2048-bit RSA or something like that. So we're a while out. But the concern is that people are today storing encrypted information and then waiting until the quantum computer, you have a quantum computer, and I don't know what it'll be, 10, 15, 20 years, you can take your pick. But then once they're able to, once you have a good enough quantum computer, you can just look through that encrypted data, and everything, relatively speaking, looks transparent from the past. And for someone, if anybody wants to keep something secret, for I think a lot of U.S. government entities, for example, it's 30 years they aim for, then that's a concern that they have now. So that's a little bit more, it's a first mover advantage.
Yeah. And like, if we go down that path a little bit, that could lead to like a variety of ongoing crises, right? Or am I overestimating the importance of our ability to keep certain information encrypted?
Yeah, it could be a really big problem. But I since we're on the podcast and I'm just speaking for me, so I get to really say my view, which is I think it'll get fixed. I think when we look back 100 years from now at the invention of quantum computing and the arrival of the quantum technology industry, we'll see a whole bunch of enormous economic benefits and this really big Y2K bug upgrade that we all had to do for crypto that was painful. And maybe some people made some mistakes and didn't do it, but like, I think the 100-year view is that we'll go through that. And one of the reasons I have that view is that there are alternatives. There are approaches that NIST has been working on a standard for a while now, and they're making some recommendations for what we call post-quantum quantum secure cryptographic schemes that run on regular computers. One way to fix this is actually to use quantum networks and quantum technologies, which we can talk about too. But even if you stick with regular hardware, there's reason to be optimistic. the execution, getting these things deployed, it's like upgrading from Windows 95, which I think some people still run. There's risk in that kind of thing. But net on net, I think some people will make a lot of money providing those solutions, and there's reasons to be worried about if you really want something from now to be secure for 50 years, you should be a little worried. But that's going to get washed out in sort of the vast advantages that you get from using quantum computing and other kinds of applications. That's my view.
Yeah, that's my view as well. In fact, that is my view exactly. That we will come up with fixes, and they're not yet readily apparent, but so are a lot of the advantages that we will enjoy when we do have truly quantum computers online, a variety of other aspects of science, of business, etc. So I am troubled sometimes by the knee-jerk view of many. You see it right now in the debate around AI, for example, where they kind of freeze knowledge as of now, and then make all of these, to me, outrageous claims about, we're all going to be turned into paper clips or whatnot. And what they're ignoring here, of course, is the new knowledge that will be generated and will be acted upon, right? And I see something very similar happening with encryption through the quantum computing era. What's your view? Is that just, I kind of view it as a bug in human OS, where we fail to think about the idea that there's a lot of options which are not currently on the menu because they haven't been invented yet. But we do have a very long history of, as you led into our discussion, innovation upon innovation and the more we learn, right, the better the tools that we make, and that's an ongoing process. Am I too cavalier in that attitude?
It's hard to say about it in general, but there's concrete downsides are people overweight them. And you can see a concrete downside of, someone's going to hack into my bank account. Upsides that might be very big, like the advances that come from custom designed quantum metamaterials, that, it's an ups and upsides. So we're weighted against it because we like downsides more. And it's also it can seem a little vaguer. And so people have sometimes some trouble balancing those. But, in our space, I think we're in a pretty good spot. The cybersecurity community has been worried about this for 20 years. We're coming up on 30 years, really. The field's getting a little bit older, and taken it very seriously from the beginning. And so I think my concern now is that there might be, as the field grows and sort of gets a little bit more popularized outside of the experts who've been tracking it, there might be an over-rotation when I think the real national security implication is not having the economic benefits of this technology happen.
Yeah, I agree. That leads me to the whole idea of open versus closed source. You specifically are looking to create an open source ecosystem. Talk a little bit about why you find that to be the more beneficial of the two paths.
Yeah, so maybe it's sort of worth saying. So I started the Unitary Fund about 5 years ago when I was at a quantum computing startup called Rigetti, and when we were starting at Rigetti, we were building some of the world's first quantum computers, and one of the things we had to solve was a credibility issue. Like, people didn't really believe what you were building. It's like that's a real thing. And one approach to solving it was by saying, well, look, we'll open source the programming toolkits and we'll put the computers online and just like let people see a little more open kimono what these things are. And when we did that, a couple interesting things happened. One is that we got contributions from usual suspects, Harvard, Caltech, and PhDs, whatever. But we also got contributions from hobbyist software engineers in Eastern Europe and students in India and high school students in Canada. And they were building, so they were finding, not necessarily new quantum algorithms, but you got API bugs, and when you make the software available for people to work with, then they can learn more quickly than if you make them march through the math in a textbook. I think learning quantum computing, what I'd recommend more than a textbook is to go take a look at some of the open source platforms, things like Qiskit, which IBM's done a bunch of great work in building up. There's actually a Qiskit textbook. So if you want a textbook to go with your programming library, you can have that too. But these things are a lot more interactive. And that actually, and it's becoming a long story, but I myself, I didn't have any of these tools. And so when they started to come up and it started to become obvious that this was potentially a more accessible space than people would think, I eventually taught a class at Stanford based on quantum programming for undergraduates who hadn't taken, senior undergraduates and master students who weren't from a physics background. The prereqs were linear algebra and Python. And with linear algebra and Python and some of these open source toolkits, you can actually get pretty close to the cutting edge in some real engineering problems in quantum computing. So those experiences have led me to, I think of them as evidence of the broader philosophy that quantum computing is a hard problem, really hard. And so we need as many smart people as we can get working on it. And we need to give them on-ramps into the technology that are not do a 5-6 year PhD. And as someone who did the PhD route and then writes PhD quality code sometimes, I also know that that's not even the optimal path for a lot of the engineering kinds of problems that we need to solve. And so we need ways for really talented engineers in control electronics and technicians and cryo and all sorts of things. We need ways for them to understand what's going on in the space. And my view is open source technologies is one really great way to do that. So the first one is just kind of growing the first reason to do open things is just to get more people involved, which will help advance things quicker. And the second is that this is a really hard technology and we need to show progress. And progress is based where we are. Progress is not just watching revenue go to the moon, so to speak. It's going to be a little more complicated than that. We need to show that we're making progress on basic technical milestones, which we're still, I was just at there's a Quantum Economic Development Consortium, which is an industry group in the US. And I was just at their plenary meeting yesterday talking about standards and benchmarks. And we don't agree. But what I push for is let's try and make what we are benchmarking, at least be transparent about what we are benchmarking and make that stuff available. And that way investors and end users and people who are seeing the space can see the progress we are making, even though quantum computers aren't solving all the problems that we wish they could solve yet. So growing the workforce, getting more people involved, and also being transparent about the milestoning and progress for a very long lead technology are two reasons why I think being open is incredibly important.
Yeah, and I'm very in favor of open source as well. And historically, Linux runs the web for the most part. Open source technology that many corporations were trying to demonize when it first came along. Are you seeing any of that from more proprietary groups? Are they trying to fight against the open source, or are they playing nicer than maybe some of the AI groups that are duking it out right now?
Yeah, these things go in waves. AI was kind of academic and open, and more recently, people have started to close out. So it started closed, got more open, it's getting more closed. In quantum, we're pretty open. Part of this is because we got in early with making that kind of a norm. And second is that people recognize the things that I was talking about. You have a lot of hardware vendors, for better or for worse, feeling like worried that they're building a hammer looking for a nail, and they really want to make their programming toolkits as accessible as possible. The core IP around how do they make the hardware, that's proprietary stuff, and people compete on that all the time. Actually, even there, you'd be maybe surprised about some of the transparency. But in many ways, it's because we're like a rising tide helps all boats kind of thing right now, where everyone knows we have a long way to go, and trying to grab too much of. I mean, it's hard to grab too much of the like, let's say, user base right now, because nobody has a quantum computer that's super performant.
Right, but my guess is that people, as it gets closer, will attempt to grab more places on the value chain from that, and hopefully the work of the open source community will continue, even as those stakeholders try to plant their flag on a particular part of the value chain.
Right.
I want to talk a little bit about the experiment that actually we really kind of bonded on when you joined me over here, and it's called Wigner's Friend. Would you outline first for our listeners and viewers what is Wigner's Friend and why is it so deviously complicated?
Sure. Yeah. No, happy to. So maybe just to frame a little bit for people who are listening what we're talking about, we've talked a fair amount about the kind of economic, practical applications of quantum computers, but there are also scientific applications. And you can think of a quantum computer as a very well-controlled, very large quantum system that you can use to study questions that we have about quantum mechanics. And we still have questions. So there's, in some ways, there's this 100-year-long history of quantum mechanics consists of someone saying, well, it consists of a lot of things, but one of the ongoing themes is someone saying, quantum mechanics predicts this really weird thing about the world, like that, particle and wave at the same time. And then people come up with some sort of thought experiment, like, oh, there's a double slit, or I'm going to put a cat in a box, or something. And then we argue a bit philosophically and in theory about the interpretation of that thought experiment. And then a couple decades later, our technology gets good enough to run it. And not, do a double slit experiment where we don't just imagine that there's an observer looking at one of the slits. We actually have a device that acts as an observer, and we see the decoherence happen. So, and then invariably, what happens when we run this experiment with the better technology is it turns so far, in ways that are maybe disappointing. So far, it turns out quantum mechanics has been correct. And maybe the most striking recent example of this was the Nobel Prize in Physics from this past year, which was given for confirmatory experiments of these things called Bell inequalities, which are so in the 60s. And if you want to read more about this, there's a book called How the Hippies Saved Physics. In the 60s in Berkeley.
What's so funny is I just opened that book. Anyway, continue, please.
So in the 60s, this guy John Bell sort of took a bit of a look at a question about quantum mechanics, and the question is something that had vexed a lot of people for a while, but it's sort of a more formal version of do parts of the world have properties that are fixed, separate from how you look at them? And you can ask this question. One of the things that I want to point out about this question is it's not necessarily a question about quantum mechanics. It's a question about any theory of physics. It's just about how reality might behave. It turns out quantum mechanics says the answer is no, but you could have other theories that say the answer is yes. And so a term for this statement, and the formal statement is, is reality described by local hidden variable theories, so any kind of physical theory that has local hidden variables, plus some other assumptions. You can call this a question about experimental metaphysics. So metaphysics is not just about one physical theory; it's about a bunch of them, and it's experimental because that question can be turned into a series of experiments that you run, and you do some statistics on them, and you see whether or not an inequality is violated, and it'll tell you the answer. And if you use the predictions of quantum mechanics, then you predict that you'll get a violation of the inequality this bound that you should get if your world is described by local hidden variables. Anyway, this experimental metaphysics term I learned is a theoretical physicist named Eric Cavalcanti, who's written a bunch about this. He's in Australia. So long and short of it is, the predictions that quantum mechanics and reality violate local hidden variable theories was made in the 60s. People started to run experiments. Initially, when they were running experiments, nobody cared because some people said these experimental metaphysics questions are not physics. But lo and behold, a few decades later, and in 2015, some really, really serious large-scale versions of these experiments, we call them loophole-free, closing a lot of the, basically dotting the I's and crossing the T's, were run. And then a couple of folks won the Nobel Prize for those experiments last year. So to come back to your original question about Wigner's friend, Wigner's friend is another one of these. And as we get better at building quantum technologies, we should go back and revisit which of these strange theoretical implications that we see in quantum mechanics we might now be able to make experimentally accessible. So Wigner's friend is one of these, also from the 60s, from Eugene Wigner. And the very, very basic way it was originally formulated is about what happens when we put quantum mechanical systems in superposition. So in quantum physics, like a quantum bit that I was talking about, it's not either 0 or 1. It can be, so 0 and 1 are the poles of that sphere that I was talking about. It can be either 0 or 1 separately, but it can be anywhere on the surface of the sphere. And those are these mixtures of 0 or 1 at the same time, in kind of a generalized way that like a flipping coin is a mixture. Now, the difference between those two is that a flipping coin is a mixture just because you don't know something about its state. Like if you really tracked the way the coin was flipping, you would know that it's going to be 0 or 1 when it hit the table. A quantum bit is different. There's no internal thing to track. It's at the end of the day some mixture. Okay, so Wigner's friend. Jim, you're going to be Wigner and I'm going to be the friend.
Okay.
So you're going to put me in a box, and you're going to take a photon that's going to be in one of these superpositions of being 0 and 1 at the same time. And so that could be like photons, when they go through the air, they spin clockwise or counterclockwise. Let's say it's that. And this box that I'm in leaks no information out. Like it's really very sealed. And so what you do is you send the photon into the box to me, and then I'm going to measure this photon. And from my perspective, when I measure the photon, it's not going to be in this mixture anymore. It's either going to have been spinning clockwise or spinning counterclockwise. So I'll either write down on my piece of paper, I'll measure it, and I'll write down it was counterclockwise, I'll write down a 0, or I'll see it going clockwise, and I'll write down a 1. So that's from my perspective what happens. Now, what happens from your perspective outside the box? Well, what's gone into the box is this photon that's some superposition of 0 and 1. And then you see me make a measurement. Well, you don't see me, you know I do because nothing leaks out, but you infer that I did. And so that means that inside of the box, from your perspective, there's actually a superposition of two different branches or worlds. One world where I will measured the photon as clockwise and wrote down 1, or counterclockwise and wrote down 0. I think that's how I did. And the thought experiment, the sort of original suggestion by Wigner, is to ask who is right. Like from my perspective, there's no superposition anymore. It's either 0 or 1. But from you just sitting outside this box, it's still in a superposition of both. And that seems like something that shouldn't be relative. I mean, those are different they're different states quantum mechanically. So how can that be relative? So in the last couple of years, people have picked up this. It was written in like relatively philosophical language originally. Have picked this up, and they have some excuse me, some different physicists. There's some folks at Renato Renner's group, Czesław Bruckner in Vienna, Howard Wiseman, Eric Cavalcanti, Elora Riefel, have and Veronica Borkman, different collaborators of theirs have been working on formalizing this thought experiment into inequalities, like these Bell inequalities, but they're called local friendliness inequalities. And basically one of the there's a bunch of ways of actually formulating them. But I can give you sort of the headline of maybe one of the simpler ones. So there's a paper by Hadara and Cavalcanti called something like a possibilistic version of Wigner's friend experiments. I think something like that title. And they make, so the setup is you make two assumptions about, these are metaphysical assumptions, right? Kind of like local hidden variables. The first assumption is that if an event happens, it happens for all observers. Loosely. I mean, they do it more formally. I'll just give you the looser version. If an event happens, it happens for all observers. And then the second assumption is something called local agency, which means that I can make independent variables. There can be independent variables that are uncorrelated with other regions of space-time. And at its core, this second one of local agency, if you violate that, you start to violate things that let us do science, because you sort of need to have reliable independent variables. Otherwise, a response to any experimental paper could be, you uncovered nothing about the physical laws of the universe. You got that outcome because there was a solar flare on Alpha Centauri last Tuesday or something. I don't know. There's like some hidden correlation all over the place. You could try and rule it out slowly, but so anyway, there's these two assumptions that seem reasonable. The first is called absolute of observed events. The second one is called local agency. Together, we call those local friendliness. And if you set up a version of this Wigner's friend experiment, not with one friend in a box, now with two friends in two boxes and a little bit of detail, then you can show that predictions of quantum mechanics say that those assumptions should contradict each other. And you have to drop one of them. And they both seem pretty reasonable. So, well, maybe I'll pause there. But yeah. When I started reading about this, I was like, oh, this is, yet another one of these really intense questions that quantum mechanics raises for us about how the world might behave. And gosh, we should probably test it.
I agree. And to even simplify it more, it seems that you've got to give up something. And you've either got to give up objective reality, number one, or you've got to give up free agency, right? One of those two, if we get to conduct these experiments, is going to go, right?
Yeah, I mean, it looks like it. I mean, yes, and it's important to mention this. The objective reality we're talking about here is not. It's not an objective reality like we disagree about some subjective thing, in language. It's really something about physics, and it's not like in relativity. Like in relativity, we will disagree about what time something happened because one of us, might be in a gravity well compared to the other. This is whether we disagree about whether or not an event occurred at all. And Eric Cavalcanti has this amazing phrase for what these little different realities are, and he calls them Wigner bubbles. And so the idea is that one of the questions is, can you create these Wigner bubbles? So these little, it's sort of loose language, but these little mini universes where events occur for the observers in them, but not for people outside. And the terminology is so great because it also lets you have a sense of why this experiment is so hard to do. These are very fragile bubbles. if any information about what's going on inside of the bubble leaks out to observers outside of it, then they kind of pop, and this violation doesn't occur anymore. And so that's why, at least naively, well, not why, but that's a way to see naively why these experiments might be tough to do.
And where are we in terms of, our ability to actually start doing these with some verifiable information as a result of the experiment?
So there's, the thought experiment, as we've described it and discussed on this podcast, involves a person in the box, and you need to have a bunch of control over a person, and people are big and hot and heavy and complicated by a lot of information theoretic measures, which make them tough to turn into quantum mechanical states. Fundamentally, we should be quantum mechanical, according to textbook quantum mechanics. Everything is. It's just that when they get big and complicated and heavy and hot, those quantum mechanical rules average out. So mostly the things that we control that are as quantum systems are small and light and cold. So what we've been talking with a few folks about are imagining a series of experiments where at one end, you do the whole darn thing with a person or two people actually in these boxes, and I have no idea how to build that. And I if anyone does, like that's sort of like a very the technology to do that is difficult to imagine. But at the other end, you run the experiment, but you replace the friends in the box just with single photons. So in this case, you sent in a photon to the box and I was in there doing a measurement, but replace me with just another photon, and the two photons interact, or something like that, or another photonic qubit. So that experiment actually was run. Sort of two groups have run a little bit of this experiment. The Nora Tischler's group in Australia ran it and saw the violation. So there's kind of this spectrum where the observer is a single photon, and at one end, and at the other end, the observer is a person, and you can sort of march up from the smaller to the bigger. And at each stage, you want to ask yourself what your experiment has actually shown you. So let's look at this first example with a single photon. One reaction is to say, pat yourself on the back and say, job done. We have shown that reality is not objective. We violated the inequality, and then we should probably go for a drink and think about the implications.
Or maybe even two drinks.
Yeah. Maybe an alcoholic one, because I want to keep it like there's a lot. So, but another response is to say, look, you put photons in as to replace friends, and photons aren't observers. You could argue that. An observer, kind of what's one of the fun things about these Wigner friends experiments is they have these inequalities that they get to about these basic assumptions, but they also start to butt up against some of the open questions people have about quantum mechanics in general, like these things called the measurement problem. And there's kind of often when quantum mechanics is presented in a textbook form, there's two sets of rules. There's a set of rules, which is the Schrodinger equation broadly, that describes how everything behaves. And then there's this other rule for measurement of observers. It's like when observers make a measurement. And practically speaking, we know how to work with these in the lab, usually. But there's no definition of an observer that is provided. We just say well, when I look at it, or when I use a device that to me looks like a measuring instrument, then I say that's doing the measurement rule instead of the other rule. And so one response to the Wigner's friend experiment with photons is to say, those don't count as observers. So the reality that observer had isn't real. It doesn't matter. It didn't have it wasn't an observer, so it doesn't have a reality. So there's no interesting metaphysical applications. And so if someone says that, then you come back and say, okay, well, but what for you is an observer? And then they might say, okay, it needs to be two photons. Probably not. They'll probably say it needs to be something bigger than that. But, maybe they'll say something about some maybe it needs to have some amount of mass that they care about. And there's some threshold of mass above which they believe the superposition will collapse because remember how information can't leak? So imagine if the friend inside the box is heavy, and if you measure 0 or 1 determines whether or not you're on the left-hand side or the right-hand side of the box. If that's true, then outside the box, I can detect how the gravitational field shifts because of what the observer measured. So the information leaks out. And so we might say that there's some fundamental collapse that happens due to gravity when something gets hotter. So they'll say, okay, I'll believe you when you run the experiment and with something that's heavy enough. And so maybe we work towards that and we run it with something that's heavy enough. And then one of two things will happen. We'll either get the violation, in which case they will have to accept some drop local agency or drop objective reality, or we will confirm this collapse model that when something gets heavy enough, it isn't, it's not acting in superposition anymore, that we have some definition of an observer that we can agree on. And it doesn't have to be something that's heavy. There's other things you could argue about, information theoretically when it looks like branches occur in quantum mechanics. And so the program we've been thinking about is to start with this great experiment that Nora and collaborators have done with one photon, and start to march up to bigger and bigger experiments and sort of rule out, either find out that something is an observer and there's a collapse, which would be a big deal, or get more and more evidence that objective reality is violated, I think is really one way to think about it.
Speculate for me on, these are two very big outcomes, right? I mean, if you have to basically agree that objective reality, we have to give up in the very technical sense that it got violated through this experiment, or we have to give up the idea of agency and I guess, I don't know, I don't want to extend the metaphor too much, but free will. In other words, it would essentially say that the universe is entirely deterministic. Am I right in that assertion?
This gets to sort of subtle points, but people who, often people who drop that local agency assumption are called superdeterminists. So these things are related, but it is subtle, and I don't know what free will is, but I do know what local agency is. We can define that, but it is also still weird to drop that. Yeah.
So the speculation I'd like you to give me is, under each of these, let's assume that we have to drop the first one, and we have to give up, in quotes, objective reality, or conversely, we have to drop the second one and take the superdeterministic point of view. How does that change, the trajectory of where we are going with the science?
Gosh, yeah. I mean, I don't even. we haven't even spent too much time thinking about that because it's definitely in speculative territory, and I should probably sit down with if anybody knows Greg Egan, he's the science fiction author I'd love to sit down and talk to about this. He just read some amazing hard sci-fi. Look, if we succeed at creating something that looks like a Wigner bubble, I don't know. I guess the answer is we're reaching the limits of my imagination. I mean, here's one thing that comes to mind, basically, which is, that Arthur C. Clarke quote that any sufficiently advanced technology is indistinguishable from magic. And if we went back 400, 500 years and we showed people some of the things we can do with electromagnetism today, like talk to a piece of glass and have it talk back, then they would just look like magic. And we wouldn't fault them for not having enough imagination to connect the dots between lightning and basic batteries and that. And I think what we're getting at with quantum computing and quantum technologies more broadly, because there's things in sensing and networking too that we haven't talked about too much yet, but that are really exciting, are also just hard to imagine where we're going to get to in 400 years. If we're really able to create little realities, like movies are going to get even better. like, I can't imagine the technology to even do with one person today, but that doesn't mean that like 1,000 years from now, it's not going to be something that's ad supported.
We'll figure a way out to monetize, is what you're saying. And I actually agree with that one. Let's chat a bit about what you just mentioned, which I'm utterly and always fascinated by, which is the movement of understanding ourselves, our sciences, etc. And the Arthur C. Clarke quote is very apt, right? Because if we even made it current, right, and we went back to just say when I was 10 in 1970, and I brought this bad boy with me. I'm holding up an iPhone for our listeners. People would I think, be able to understand the concept that this was a communication device, because after all, Star Trek was on the air in the late 60s, right? And so maybe they'd make that leap and say, is that a communicator? And get it. But the reason I use that example is, like, for many people, 1970 is relatively, not that long ago. When we extended to like 500 years, right? Of course, 500 years ago, we didn't have any of this, right? But I think that even if you went back to a relatively recent period with some of our existing technology, I mean, if you really wanted to blow minds, you'd go back with GPT-4,
Sure.
and show them that. Is there a process? And again, this is a very speculative question for you, and you can simply say, I'm not going to speculate on that. But is there, as one of the things that a thesis that I have is that we have become and are getting better at abstraction. And as we get better at abstraction, we are able to contemplate things like Wigner's friend in the very beginning. I don't know if you're aware of the IQ researcher Flynn, who's got an effect named after him. So he started looking at normed IQs from, I think, 1900, and then from recently, he died. So whenever he did that before he died. And what he found was a consistent and persistent increase in IQ. Now, they always renorm it to 100 on Stanford Binet, right? But if you didn't renorm it, if you just looked at the raw scores, you would see that IQ had increased relatively significantly from 1900 on. And he was fascinated by that. And one of his theories was that in the world of 1900, naive realism was still pretty much dominant in, even educated lay people. Now, it wasn't in scientists, and it wasn't in a certain group or groups of people, but in an educated layman, naive realism was still pretty much what they looked at the world through that lens. And his theory was that as we learned more, quantum mechanics and physics being a big part of the increase of people's ability to understand abstraction, he said that allowed for our ability to continually push that barrier forward, right? And because we could now abstract, we could construct an argument, whereas the world of things, so to speak, of 1900 was giving way to this world, which is far more abstracted. Do you think that there is an upper limit to what we humans can achieve under this kind of regime, or much like we saw with Flynn, are we just going to continue to be able to push the boundaries further?
One could say something about big theoretical limits on like if you have enough information density, then you like fall into a black hole, kind of thing. But I'm not sure that that's the direction I want to go with what you're talking about. Because I think I wouldn't know if I would agree on the naive realism. By the way, I mean there's a lot of I don't think any like a lot of religious and spiritual cultural things are definitely not naive.
True.
Or big guy. True. But I do think what has started to happen in many ways, technology is a integration of mind and body. We're taking what our desires often and putting them into the world and in a way that connects what we are internally with what happens externally. And one example of that is people talk about, well, what's going to happen when we have mind uploading or when we have extended consciousnesses. But we have extended consciousnesses today. If you get rid of everything, my phone and my ability to have telepresence and all this, I mean, I'm here and with you and will be with other people in this recorded podcast. My memory is definitely stored in many, many different bits in many, many different data centers that I would be a different person without them. So as technology advances, we are integrating ourselves into the world through applied physics and chemistry and biology. And quantum is one direction of that happening with very, very weird and unintuitive versions. And I think one of the things that's most special to me about quantum technologies is this integration of mind and body often seems like it might be one way. I think people naively think it's one way. It's we have things we want to imagine. We imagine inside of ourselves. We want to build them in the world to take care of us and to take care of the people that we love. And like only if like physics didn't get in the way and mean that it was heavy and energy expensive and all this kind of stuff. But quantum mechanics is the opposite. It's not that quantum computers are saying, here's all these limits to the computers you could imagine building. It's actually saying, I can do things that you don't understand what it's computing. Like, that's your challenge. Like, think of this as a computing system and these rules that you didn't imagine exist and figure out how to use them. This analogy doesn't just apply to this kind of two-way of nature reflecting back on us. That doesn't just apply to quantum mechanics. I mean, a lot of the reason I think we have trouble with climate and nature is we're not listening. To a lot of other kinds of complicated systems that have rules that we don't understand ecologically or biologically. But quantum is a very, very striking version of it. So anyway, maybe there are some limits, but we're gonna change reality, and reality is gonna change us at an accelerating pace.
I love that answer because you highlight the fact that many people often don't even think about. And that was in your response to, we already have that extension, right? There are bits of you in various systems that we have that we would have never had, right? So I think at least I hope for our listeners and our viewers, they're going to be able to think, oh, I never thought about it that way. Yeah, that's quite true, right? And one
and a little part of me is also in them, or the little part of someone else that's me that gave me that thought that is them. It's the usual.
Yeah. But when you put it the way you did, it makes it more practical. At least to me, it makes it more graspable to a practical understanding of. Yeah, that's already going on right now, and we're just going to see an extension of that. I'm a fan of David Deutsch, who wrote The Beginning of Infinity, and he made an assertion that I want to get your reaction to, which is anything that does not violate the laws of physics is true. What's your reaction to that?
It's an interesting question to ask. I mean, my immediate reaction is we don't know what the laws of physics are.
That was my immediate reaction too.
Yeah. So, we have some rules of thumb that apply in different kinds of circumstances pretty well practically now, but they're very different from what we thought they were 100 years ago. And I think it would be naive to think that we have the answer now. And so something comes after quantum mechanics, and it's probably, one thing I will probably bet on is it's not going to be more intuitive. It's probably going to be more weird. And so we would change ourselves more to understand it. So that might be the case. I mean, another reason that's hard is what it is to have a law of physics is also a historically contingent thing. Maybe I need to ask David what his definition of law of physics is there. But one of the interesting
actually, to be fair to Dr. Deutsch, he did. I gave the last little line of his statement. He did preface it by saying the laws of physics are always changing, and hopefully we are adding to our understanding of them. But that's where you sort of the whatever doesn't violate the then understood laws of physics is true.
I see. Yeah. So then truth becomes, there's this fun book, which we won't have time to talk about, by a philosopher named Ian Hacking, who unfortunately recently passed away. And the title is Historical Ontology. And I think that's kind of what we're talking about here.
I love that. I'm going to pick that book up. So thank you for the recommendation. So what's next for you? Like, in the applications, you did an excellent job. And, were an easy choice for us. But one of the things you did a really good job on was in our application, we asked, what are the implications of if what you're using this grant for fail? And you gave a really great answer. In fact, probably one of the best that we saw. A lot of the ones that we got didn't really dig in like you did, because what I loved about it was your attitude of how much you can learn from failure. And so, what do you hope? What's next over the next, the balance of your fellowship and then beyond? What are you going to be hoped for milestones?
Well, in the context of trying to figure out how to run something about Wigner's friend, there's a bunch of exciting failure, I guess. I mean, so really what we're trying to do next is first off, make sure that the basic theory all makes sense. In a couple of the papers that have been put out over the last couple of years, talk to some more people, kind of get a little bit broader circulation. And secondly, come up with fundable milestone experiments. And understanding what a good milestone is starts to get to theoretical questions about what makes an arguable observer. And that's a fascinating question. We've got a couple ideas. There's lots of people who are working on different kinds of things related to this in quantum information. And then the second bit is fundable. So what can we actually build that is a definition of an observer that makes sense? I mean, one direction you could go is it's a biological system where it has consciousness. So we'll put something else that has consciousness in there. And I also don't know how to build. I don't know how to put things that are in consciousness in the superposition. If anybody knows, who's a listener, knows what is the smallest arguably conscious biological system, smallest in physical scale, I'd love to get their take on that. But even still, that's tough. So the real milestone that I'm targeting next, in terms of Wigner's friend, is picking out some specific, well-defined milestones that can have a budget against them, to go and build things that are bigger than a single photon, but a lot smaller than a person, but still be meaningful. And yeah, if we fail, it's because we broke the theory, which would also be fascinating. Or we fail because it's really not fundable, and we just don't have enough technology as a species yet to do it. But one of the things, I actually haven't mentioned this so far, so I should. But one of the things that I'm thinking about is putting quantum computers in as observers and having them run programs. Right? I mean, quantum computers are big quantum systems that you can control, where big can have a bunch of different definitions. So that's a direction that we're pretty excited about, piggybacking on a lot of the industrial investment that's gone into quantum technologies, and will continue to.
Very cool. Well, this has been absolutely fascinating. As you know, this is like catnip for me. And I'm delighted to see the work that you're doing, and all of your colleagues, as well as your foundation. I think bringing this all together, exposing it to the most cognitively diverse group of people, is the way to gain footholds that you wouldn't otherwise. So I think that your strategy is bang on, and I'm delighted that we can be a small part of it. At the end of our podcast, this will be a really interesting one. We always ask people, okay, so we're going to have a thought experiment, and we are going to wave a magic wand and make you the emperor of the world for one day. You can't kill anyone. You can't put anyone in a Faraday cage, and you can't put them in a re-education camp. But you can. We're going to give you a magic microphone that you can speak two things into. And the next morning, whenever the next morning happens to be, for the 8 billion plus people on the planet currently, they're going to wake up, and the two things that you incepted them with, they're going to think were their own ideas, and they're going to say, you know what? I'm going to act on both of these starting today. What two things are you going to incept in the world's population?
So it's like a big communicator rather than emperor power. It's just the bully pulpit. Oh man. I know where the first one is. Let me think about the second one. I don't know. Maybe it's a bit glib, but we could talk about it more. I think the first one is learn quantum mechanics. I really mean that. I think it's like I don't know. So a lot of people in our field, go through a bit of it's a sort of a breakthrough moment when you realize that the world is like that, and there's a humbleness that you have to take on to realize that it's not only is it is different, it's very different from what you thought, but even at the very, very core fundamental level. So number one is learn quantum mechanics. The second one is probably spend more time with your family.
I actually love those in connection with each other. I think that the world would be a much more interesting place if both of those got incepted into our population. Well, listen, this has been a tremendous amount of fun for me. Thank you so much. We will include in the show notes all the books mentioned and the various websites where people can find you. And thanks for being with us, and thank you for being our first fellow.
Oh, thank you, Jim. I mean, there's a bunch of stuff that can get funded around normal paths easily. Incremental academic papers or the next generative AI startup. But there's stuff that falls through the cracks. And often those are the really exciting and interesting things. So I like Wigner's foundation experiments or some of these open source quantum public goods. So thank you for that support. And then I guess the last thing I'll just say is, if anybody's looking to get involved in quantum technologies, Unitary.fund is the website, and we do a bunch of open source stuff. We just concluded a big hackathon. Might be easier than you think if you're technical. Prereqs are basically Python and linear algebra for a whole bunch of things. So I hope to see some of you there.